My chapter 13, your chapter 15 in brown covers chemical equilibrium. And the reason we put equilibrium after kinetics is because of what's required to produce an equilibrium. You can look at it two different ways. You can look at it from the macroscopic, from what can we actually measure at our level, and then what's going on underneath at the microscopic level. The macroscopic level, when a reaction has reached equilibrium, we can write it this way.
Not more A's.
Yeah. Well, there's a C and a D in here too.
Yeah.
Reactants to products goes at one rate, right, with our rate constant. And then once you start building up some of these, you can get a reverse reaction at even a different rate. And once they reach equilibrium, the forward rate equals the reverse rate. And okay, at the macroscopic level, what you see is nothing's changing. Concentrations here are stable, concentrations here are stable. But what's going on underneath is these things are going at a furious pace, right? As soon as you get some over here, they go back. But the rate that they go forward equals the rate they go back.
So it's really not changing.
Right, it doesn't appear to change. And that's why we put kinetics first, because the discussion of rates.
One slower one I thought was going to be the rate. What kinetics was.
Yeah, when we're talking about mechanisms. But this, when we talk about equilibrium, lots of stuff can go on here. All we're concerned about was here and here. But with kinetics, we're looking at this part right in here. You're not alone. Okay. So we've got these two possibilities. The macroscopic looks static, nothing's changing, but the microscopic is dynamic. Things are happening at a furious pace. And this is one example. This is the one way to represent at the very beginning, right? You have no ammonia at all. You have some nitrogen and some hydrogen here. And, but over time, you start building up some of this product and you get the reverse reaction to where now you reach equilibrium when the concentrations are stable. And that's just telling you the same thing I told you before. This is another way to look at it, where the forward rate is very high and the reverse rate is 0 to begin with. That's why we do the initial rates method for determining the constants, is so that we don't have a competing reverse reaction. So we're actually looking at what is the rate of the forward reaction. If you want to study the reverse reaction, you just flip your equation around and now make the products reactants, and then you put the reactants in and make the products to go the other direction. And you can get some idea about the reverse reaction also. But at some point, they merge. Okay. Consider an equilibrium mixture in a closed vessel. We've got water reacting with carbon monoxide to produce hydrogen gas and carbon dioxide. Now, it ought to be obvious that you have to have a closed vessel for this to happen because they're all gases. So what would happen? You're at equilibrium now. What would happen if you add more water? Hydrogen and carbon dioxide, yes. If it's balanced, I mean, if it's equilibrium, and then you do something like add or even take away one of these, then you change the reaction dynamics on the microscopic level, and it has to adjust. Okay, so if we do the same thing only on this side, just add more hydrogen, it'll go back the other direction until we reestablish equilibrium. Once you reestablish equilibrium, then things don't change anymore. Okay. This equilibrium situation can be quantified, and it's based upon this law of mass action. It was proposed first by these two Norwegians, Peter Wade and his brother-in-law, Goldberg. And it happened in the middle of the 19th century. What they were trying to do was derive a mathematical description for what they were trying to find out what drives a chemical reaction. There was starting to be interest about this time in entropy. We talked about entropy in the first semester. They went off in this direction, and other chemists went off in the direction of entropy. But with their research, they found that if they expressed an equation, let me skip that. And they based their work on concentrations of the reactants in solution. Now it doesn't have to be in solution. You can say concentration of various reactants in a gas too, because molarity just means moles per liter. So if it's moles of gas per liter of the container size, that's a perfectly valid expression for its concentration. But sometimes if we're talking about gases, we'll say partial pressures instead. It's easier to work that way. Okay, so if we have this hypothetical reaction, and we have, these are the coefficients, the little letters are the coefficients for each of the reactants. This is a balanced equation. Remember when we said we cannot derive the overall kinetic expression for a reaction based upon the balanced equation, right? We can just do the individual elementary steps. We can do that. But for the overall kinetic expression, rate expression, it has to be empirically determined. This is different. Law of mass action you can get directly from the balanced equation. And all you have to do is make the numerator the product of the concentrations of, in this case, C and D, and then raise them to the coefficient power. And then divide by the reactants, product of the reactants raised to their respective powers. That's the mathematical expression for the law of mass action, and it's equal to a constant value at a specific temperature. If you change the temperature, you change this value. So you can have the same concentrations, but the K will vary. Well, I didn't say that in here. We'll let it ride for the moment. The other thing is the square brackets. That's standard notation for equilibrium concentration. So the equilibrium concentration is what you want here, not what you start with. But once it reaches equilibrium, what is the concentration of each one of those? Then you can plug those values in to the power and get a K. If we change the temperature, then it's going to shift to one side or the other. That gives us different values here. And shifting the temperature will change the value of K for that reason. Okay, let's see, one other thing. Units of measure. if this is molarity, here, 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 and here, then these could be any numbers based on the balanced equation. So you could get molarity to some weird power here and here and here and here, and you could end up with some really strange units of measure that just, the sky's the limit. So we typically, when we report the K value, we don't put units of measure. We just have to specify, where does that K come from? The K comes from that equation. And if you set it up properly, then you'll get the right answer. So if you know the K and you know 3 of these, you can find the 4th one. Or if you know all 4 of them, you can find the K. And the units of measure are set aside because they can be so complex, it's just a nightmare to try to deal with them. And if you look these values up in a reference manual, the only thing that will be specified is what were the beginning units. Did you start with molarity? Did you start with partial pressures? Did you start with some other unit of measure? And that will be given in the header for the list of data. Okay. So what if we reverse the equation? If we turn the equation over and put the CD as reactants and the AB as products, what happens to the equilibrium constant? Well, you can see from, let's see. If you flip the equation, then you put this on top and that one on the bottom. So that means that you just invert the K. Right? So if you decide that you want to go reverse, what would be the equilibrium constant for the reverse reaction? It's just the inverse of K. That's what this one says. What if you need to multiply your whole equation by some factor? Remember when we were doing thermochemistry and Hess's law, where you add equations together to find out what the enthalpy is for the new equation? Sometimes we had to multiply that one of the equations by a factor in order to end up with the correct equation for to give us the enthalpy for the total. If you have to do something like that for the equilibrium expression, now the new K is the old K to the power of that number. So if we go back, say we have to multiply this by some number. Let's use a real number. Say we have to double it. Right? What does that do to all this other stuff? Well, that doubles that one. It doubles this one. It doubles this one, and it doubles that one. So mathematically speaking, it's this expression squared, right? We factored out that square. So that's why the new K now is the square of the old K, or it's the factor. The factor is the power of the K that gives you the new K. So, and then this is just a reminder, Ks are always reported without units. So you got to be real careful about your calculations, since you don't have the units to guide you, to keep you honest. So as long as the temperature is the same, K will be constant. Okay. It doesn't matter what concentrations you start with, the K will always be constant at a given temperature. The point of this slide is to draw to set in perspective the difference between the equilibrium constant and equilibrium position. The equilibrium constant is a constant for a given temperature, but the equilibrium position can be different And that refers to what are the actual concentrations of the reactants and products. In the earlier examples, if you add some reactant, it's going to force the shift to the other side, and that'll change the concentrations of the products, and it'll also change the concentrations of the reactants. But when you do the calculation with those new concentrations, you come up with the same K, but it's at a different position, which refers to the concentrations. Now, the Ks can have little subscripts, and these are examples of some. If it's just a K, we generally say it's equilibrium constant. But sometimes we'll also write EQ in there, especially if we've got it in the same discussion with other types of Ks. We'll specify this one's equilibrium constant. There's a special one for water dissociation constant. So if water goes like that, that's a liquid. Right? It will break apart into this and this. Okay, that's dissociation. It goes both ways, and there's a constant associated with that. We'll get into that in more detail when we talk about acids and bases. Now, these values associated with a constant, they could be almost anything. They could be very large numbers. They could be very small numbers, which is an indication of whether the reaction wants to go largely to the right or it wants to stay on the left. So the size of that K value gives you some indication as to whether that reaction, which side does it prefer? Acid dissociation constant. This works for any acid. It'll just be your generic HA, right? And it'll produce hydrogen ions plus that. And there's a constant that goes with that. For each of the acids. Solubility product. Let's see. We're going to get to that a little later, I'm pretty sure. Equilibrium. Acid bases are next, chapter 14 and 15. And then solubility product is right after that. Okay. So I'll define what that means later. And then formation constant for complex species. We'll get to that too. But these little subscripts, they have a meaning. If you're using partial pressures, we'll put a K with a small p. So that gives you some idea as to what's the origin of the units. So you can write for this expression, which is the Haber-Bosch process. I think I've used that before, haven't I? Nitrogen and hydrogen makes ammonia. Fritz Haber and later, I forget the guy's first name, Bosch, modified it a little bit. Produces ammonia from nitrogen in the atmosphere and hydrogen gas. You can make this expression, if this is in molarity, then it'll look like this. Right? And if it's in partial pressures, it'll look like this. So these two values are not the same because their starting values were different. They're different units, but they are related. And we're just going to do a calculation first. So if at equilibrium, you have this atmospheres for ammonia, nitrogen, hydrogen, plug those values in, right, like that. Don't forget the powers. I make that mistake too often. I forget to cube it or square it. And then when we do the calculation, we get this value, right? 3.9 times 10 to the fourth. So what does that mean? That means that the equilibrium position for this reaction is over here. because this is the denominator. This is the numerator. Now they are related. If you know what the equilibrium constant is in molarity, then you need the gas constant, which this one is the 0.08206 version. You need the temperature in Kelvin, and you need this delta N. So what does the delta N mean? It's the sum of the coefficients of the products minus the sum of the coefficients for the reactants. So if we go back, 2 minus 4 is minus 2. So you can have a minus. So this will be minus 2. And then you'll have R and whatever the temperature is, and then stick in the K. In this case, we would put that value in, put this one, and that one in, and solve for that one. Let's see. That's what we're going to do right here. So there's your minus 2. There's your gas constant. There's the temperature. We're doing this temperature at 35 degrees. And then we calculate the K for molarity units as 10 to the 7th. So they're not the same as the atmosphere version. Okay. So we can reference equilibria in terms of, is everything in the equilibrium in the same phase? Gas, gas, gas. That's homogeneous equilibrium. Aqueous, aqueous, aqueous. That's homogeneous equilibrium. This would be an acid dissociation. Hydrocyanic acid, dissociative. I can tell you up front that it stays mostly here. It has a very, very low equilibrium constant. So it only makes just a few of those. But it'll still kill you. Heterogeneous equilibria involves different phases. So here we have a gas and a solid, or a liquid and a gas and a gas. That's heterogeneous. Now, why am I bothering to tell you this? It has a bearing on the equilibrium expression as to what the phases are. Notice that while this reaction is going on, what's the concentration of the solid? It never changes. I mean, a solid is a solid, right? So the equilibrium expression only has this term in it because these concentrations don't change. As long as there's some of them there, then that's the only one that changes. That's a pure liquid. It doesn't change either. So we're only concerned with this one and this one. So when we write the expressions, any pure solids and liquids drop out of the expression. That's why the expression for this one is only oxygen to the 3rd power. That's it. Now, if you see this and you don't see anything else, you have no idea where that came from. So it has to be associated explicitly with that reaction. All right, so this one needs to be taken with a grain of salt. Generally speaking, if the K is extremely large, much larger than 1, you can infer that the products are dominant at equilibrium. There's much more product. If it's much less than 1, then it's the other way around. Reactants dominant. But some books will say if it's 1, then they're 50-50. No, can't be, because it can't be guaranteed because of the coefficients, which give you different powers. So just because it's equal to 1 doesn't mean that you have equal reactants and products. So that's why I say much larger than or much smaller than. Then that gets around that problem, because then by the time you get really large or really small, the coefficients don't matter as much. and you can't make inferences about the reaction at that point. And you may also infer that if the value is extremely large, the reaction essentially goes to completion. You have virtually no reactants left. Okay. So if the equilibrium lies to the right, the value of K is larger or greater than 1, smaller, less than 1 if it lies to the left. Okay. So let's say we put a certain amount of reactants and products in a vessel. And we want to know which way is the reaction going to go. Is it going to move to the right as written or to the left? Right? Well, you can watch it and measure it, and that'll tell you. But say we want to predict which way it's going. What we do is we do a calculation called the Q, the reaction quotient. The reaction quotient is calculated exactly the same way with exactly the same formula as the equilibrium expression. Only you use starting concentrations instead of equilibrium concentrations. And you get a value. Then you compare that value to the K. And that tells you which way the reaction is going to move. So, need the next slide. Okay. This is the easy one. If the Q and the K are exactly equal, then you're already at equilibrium. Right? If the Q is greater than K, the system shifts to the left. Think about it. What is that expression? A to the little a, no, excuse me, I'm backwards. C to the little c times d to the little d over A and B. Okay, that's equal to K. So if we calculate the Q, and the Q is greater than K, that means this had to be bigger than it would be at equilibrium, which means you've got too much product, and it wants to shift back to the reactant. That's why Q greater than K means it shifts to the left. And the only way that this has meaning, left or right, is if it's associated with a balanced equation, right? And I'm emphasizing that point because for Le Chatelier's principal lab, when we do that, answer the questions in there. If you say just shift to the left or shift to the right, there's no reference to a balanced equation anywhere in that discussion, then it has no meaning. Left and right mean nothing. Because for all intents and purposes, you could flip the equation and say left and right and be wrong. So it needs to be associated with a balanced equation to have meaning, left and right. And then the other way is if K is greater than Q, that means Q has too little of this. It's too small, and it's going to shift to product. Now, you could say shift to product, and then you still need a balanced equation. So, can't let you off the hook there. Okay. So let's see, we've got a reaction here where we have iron 3+ ion in solution and thiocyanate polyatomic ion reacting to form this species. You're going to do that one in the lab next week. This is kind of it's more qualitative than anything, making observations. This turns out to be a brick red color, so it's easy to detect whether it's there or not. Okay, so if we consider this reaction and we're given 6 molar iron and 10 molar thiocyanate mixed together, And at equilibrium, the concentration of this one is actually 4 molar. What's the value for the equilibrium reaction? So what's your first step? Write the expression. Right? What would K look like? Right, we need this one. To the first power divided by this one. Also to the first power. There we go. So that's your equilibrium expression for that equation. That's your first step. Then you have to say, does this information, is it enough to tell me what the equilibrium concentrations are in order to calculate the equilibrium constant? So the method that's developed for this is called the ICE table. And we say ICE because, let me see, it's on the next slide. Here we go. ICE refers to initial change equilibrium. So you say, what are your initial conditions? And I like to set up the, just like this, set up the balanced equation here and then make a table underneath it for the values. So the initial concentration is 6 molar iron, 10 molar thiocyanate, and 0 product. Right? There's no product. It just says we mix those two together. So for this one, you know which way the reaction's going because there's no product. It has to go that way. These are the easy ones. So what else are we given? We're given this one. We're given this one. And we're given the final concentration of that one right here. That's the given information. So can we determine, well, we know this one's 6, that one's 10, that one's 0. And we know this one. How did this one get here? Well, it had to come from the change. We had to add that much to get there. So if that one, if 4 molar is here, how did it get there? Well, we had to subtract 1 to 1 to 1, means 4 molar lost there and 4 molar lost there. Okay. So that means these are minus. That leaves us with this much and this much at equilibrium. And then we just plug them in the equation. And now we've calculated K at that temperature. Now that we know K, we can do so much more with it, right, under different conditions. If we want to actually calculate the concentration with different position, starting position here, say we start off with 3 here and 5 there, right, and 0 here. Then we can calculate what are these values because we know this value right here. Okay, clean this up. So the ICE table is a valuable tool, and we're going to use it not just for this chapter, we're going to use it for practically everything else to the end of the semester. So in this second trial, say we start off with 10 molar, but now we have 8 molar thiocyanate. So we want to know what's the equilibrium concentration of our product. We can set up the ICE table again. This one looks a little different, but we know it's going to the right because this one's 0. Now we say, here and here. So 10 minus X, 8 minus X, and X are the equilibrium values. We plug those in here, okay, equal to that. If we solve for X, that will answer the question, how much of that is there? Okay, so here comes the sticky part. If this calculation reduces itself to a quadratic, then you have 2 choices. Use the quadratic equation. Remember, X equals minus B plus or minus B squared minus 4AC all over 2A. I've got that plastered on the back of my calculator because I never can remember it. I was lucky to get it that time. And then you'll have two values, right? Because it's plus minus.
That's, I like that.
Remember that one?
Something like that. I don't remember that equation.
Yeah. Then when you get these two values, you have to decide which one makes sense. Right? If X is 15.99, it can't be, right? Because it has to be 1 to 1 to 1. There's nothing in here about 15. Right? So that one, we cross that one out.
That's from calculus. That equation right there is from calculus.
Oh, it was derived from calculus.
Yeah, but it's the same one I had to learn in calculus back in high school. They may be driving into my brain for that whole year.
Okay. Okay. So in this case, since this value, here it is. Our equilibrium constant is 0.333, isn't it? 0.333. Here we go. Yeah. Since this value is too close to 1, then we can't use the estimate estimation type. The reason, what I'm saying is, if this value is extremely small, then we might say that we're only going to get a little bit of X, not very much. In which case we can say X is a lot smaller than 8, it's a lot smaller than 10. We can throw those out. Right? And then just solve for a simple X without going through the quadratic. But we see from this that it's going to be a substantial value compared to 10 and 8. So we could not use that estimation method. And even when you use the estimation method, if we come out with a value, you need to plug it back in this equation and be sure it comes close to that value. Okay, so if it were, I don't know, 0.1, and we plug in 0.1 here and here and here and say, does it come out to that value? And we use an estimation rule, 5% rule, is the answer you get from this calculation within 5% of the actual value. If it is, then you can go with it. We should have examples here that we can use. We can't use it for this one because that K is too big. If the K is really small, like 10 to the minus 3 or 10 to the minus 7, something like that, then usually that estimation will work and save you going through the quadratic. Okay, so for this one, well, it's not going to show us the table, but we do the same type of calculation and we end up with 3 molar for our answer. Okay, so these are just problem-solving rules. You got to start with a balanced equation. That's a given. Then you write the equilibrium expression for the law of mass action. Then you list what are the initial conditions. What do you know? Then, if necessary, if you do have reactants and products, a non-zero number for each one of the reactants and products, then you need to calculate Q and determine which way is the reaction going, because that will tell you whether your X is minus or plus on either side for the change. Okay? If one of them is 0, then you know which way the reaction is going. If you've got a reactant that's 0, then it's going that way. If you got a product that's 0, it's going that way, no matter how many of the others you got. If you got 0 on both sides, then I guess you have to do a calculation. But if you got 0 only on one side of just one reactant or product, you don't need to do the Q. You know which way it's going. Okay. Then set up your ice table and decide which way are you going. And where is your unknown value? It's best if you can set up your ice table and make X equal to the actual answer to the question, if at all possible. So once you solve for X, you got your answer. If you can't do that, then you'll solve for an X, and then you'll use that value to derive the answer. That just adds an extra step. You don't need to do that. If you can set up X so it is the answer, then that's the best way to go. Then once you find out the equilibrium concentrations, even if there are unknowns in the expression, plug them in and solve for the unknown. Okay. So we're not going to go do all these. You got plenty of examples to do in your, if we had the time and the energy. No, we got the time. I just don't have the energy to do all three of them. But these are the answers. All right, so I'll leave them up there long enough for the recording to catch them all. And then if you want to, you can go back and check. Okay. What do we got here? 2 mole sample of ammonia is introduced into a 1 liter container. All right, so we're going back the other direction. We flipped that equation, remember? Exactly right. At a certain temperature, the ammonia partially dissociates according to this equation. And then at equilibrium, 1 mole of ammonia remains. So you start off with 2 and you only got 1 left. Calculate the value of K. All right, balance that equation first. Well, you identify what's given. And, oh, it's not going to do it for us. Oh, okay. So we have to balance the equation, which means we need 2 here and 3 here.
I said announcement.
Yeah. And then you set up your ice table with ammonia and nitrogen and hydrogen here. And then you say, what are the initial amounts? 2 moles per liter. So that's 2 molar. And then nothing here. Okay. Then you have, at equilibrium, 1 mole of ammonia remains. So you got 1 mole of ammonia that remains here. And in that same liter, so it's 1 molar. So how did you get there? Well, we subtracted 1. Right, that's the only way you can get there. So that means for every 2 ammonias, you get 1 nitrogen, 0.5. And for every 1 nitrogen, you form 3 hydrogens. So it's 1.5. Right, so now we got 0.5 and 1.5. These are molar.
Is that because you divide it? Because you only did 1 other?
Say again?
Well, you put plus 0.5 whenever you said plus 1. So is that because you only subtracted by 1 instead of 2?
Well, the change, we lost this in the change. So that means it had to appear as nitrogen on that side. And for every 2 of these, you get 1 of those.
That's what I was saying, but because you only did 1 on that side, you only get half of that.
Exactly right. Yeah. And then instead of doing a 2/3 calculation, I started with this one that I know and say, all right, this one's 3 times that one. And then add them down. Right. Now we can put that in the expression and find the K. Yeah.
I like this a lot better. Looks my brain better.
Yeah, it does me too. Calculate the equilibrium concentrations of these 2. Right. So if we start off with 1 mole sample of N2O4 in a 10 liter vessel, that's a 1/10 molar, because this is 10 divided into 1. And then you know the reaction's going to the right because you put this in there, but nothing else. So you've got your balanced equation, do your ice table and your unknowns. And I would set my unknown as this one. And then you can calculate the concentration of this one, and that will be half of it. Well, no, it won't be half of it, excuse me. It will be, half of it was subtracted from the beginning. That's what I mean. Okay, Le Chatelier's principle. Obviously, the Chatelier was a Frenchman. And he formulated what we've already discussed as what happens to an equilibrium state when you disturb it. And you can disturb it in a number of different ways. We've disturbed an equilibrium situation in one way by adding or subtracting reactants or products. That you physically change the concentration after it reaches equilibrium. Then what does it do? Well, it shifts in a direction that will reduce the change. So if we add something on the reactant side, it's going to shift to consume some of that and move to the product side. Okay, that's the concentration shift. That's fairly easy to understand.
Le Chatelier's principle states that if you have a reaction equilibrium and you apply a stress to that equilibrium, the reaction will shift in a direction in order to relieve the stress. We will look at a series of different reaction equilibria. We'll apply a stress to those equilibria and see in which direction they shift. In the reaction between iron plus 3 ion and thiocyanate ion, if we add some iron plus 3 in the form of iron 3 nitrate, and to the iron 3 nitrate add some potassium thiocyanate, the two react to form a reddish-orange complex ion. We fill 2 test tubes with the reaction mixture. We're going to keep one test tube as a control so that we can see what happens to the color. To the other tube, we're going to add some 0.1 molar iron nitrate to increase the concentration of the iron. We see that there's an increase in the dark red color. This indicates an increase in the concentration of the complex ion. This also indicates that the reaction has shifted in the forward direction. As you add reactant to an equilibrium, the reaction shifts in the direction to use up the added reactant, in this case the forward direction. Now we'll add 0.1 molar potassium thiocyanate to the second tube. This increases the concentration of the thiocyanate ion. We see that the reaction mixture turns a darker red color, indicating an increase in the formation of the complex ion. We've added the other reactant, the thiocyanate. The reaction shifts in the forward direction to use up the added reactant. We will now add some 1 molar sodium hydroxide solution. We notice that the red color decreases significantly. This indicates that the reaction equilibrium has shifted in the reverse direction. The hydroxide ion precipitates the iron ion, effectively removing it from the solution. The equilibrium shifts in the reverse direction to try and increase the concentration of the iron. We will now add solid potassium chloride to the solution. We notice the decrease in color indicating that the reaction has shifted in the reverse direction. The chloride ion forms a complex ion with the iron, effectively tying up the iron concentration. The equilibrium shifts in the reverse direction to try and replace the iron that's been removed. We will now add 0.1 molar silver nitrate to the reaction mixture. We notice the disappearance of the red color, which indicates that the equilibrium has shifted in the reverse direction. We also see the formation of a small amount of white solid. The silver ion reacts with the thiocyanate ion to form slightly soluble silver thiocyanate, which is the white solid. The silver ion removes thiocyanate from solution. The equilibrium shifts in the reverse direction to try and replace the thiocyanate ion that's been removed. We will now add some 0.1 molar mercury 2 nitrate. The mercury plus 2 ion reacts with the thiocyanate ion to form a new complex ion. This effectively reduces the concentration of thiocyanate in the solution. The equilibrium shifts in the reverse direction to try and replace the removed thiocyanate.
Okay. Let's see. That was a situation where we changed concentrations and different methods of reducing concentrations on the reactant side to drive them in the reverse direction. And what we used was called a coupled reaction. In other words, we had two reactions going on there. And one where we added reactant to effectively remove one of the reactants drove the reaction in reverse. So 2 or 3 of them, we removed the iron by reaction. A couple of them we used to remove thiocyanate. So you're going to be doing that also next week, using coupled reactions.
We do this with a lot of colors.
Oh yeah, you get to see that one, the brick red one.
And probably the white one.
And the white one, yeah, we're going to have some silver in there. Okay, so that was changing concentrations. You can also shift a reaction by temperature. What temperature does is actually changes the K value. But we don't have to calculate the K to make the inferences. What we do need, what is more useful in this case, is do we know that the reaction is endothermic or exothermic? So if it's, let's see. All right. If we know that it's, let's just say we have A plus B yields C plus D again. If it's exothermic, it's useful to treat the heat generated as a product, right? Because before it was cool and now it's warm. So we have plus some heat. If we say this is a product now, what happens if we change the temperature? If we increase the temperature, we're adding that factor in and it reverses the reaction. If we do the same thing for endothermic reactions, that means the heat enters the reactants and is buried in the products. Now, if we add heat, it drives the reaction to the right. And vice versa. I mean, if we cool it down some more, then it'll move back this direction. So it's easier to make inferences based on that methodology than it is to actually calculate K. But in a chemical sense, what we're actually doing with temperature is changing the K. Okay, I think we got another slideshow coming up here.
This is MSJ Chem. In this video, I'll be looking at Le Chatelier's principle and temperature. Changes in temperature cause a change in the equilibrium position and in the value of the equilibrium constant Kc. Here we have the chemical equation for the Haber process. In the Haber process, nitrogen and hydrogen react together to form ammonia. The forward reaction of the Haber process is exothermic. This can be seen by the negative value for the change in enthalpy. If the forward reaction is exothermic, the reverse reaction is endothermic. We can see this by looking at the sign of the enthalpy change, which is positive. So when we use Le Chatelier's principle to predict in which direction the equilibrium position will shift, we need to know if the forward reaction is endothermic or exothermic. If the forward reaction is exothermic, the reverse reaction is endothermic, and vice versa. Next, we'll predict in which direction the equilibrium position will shift when the temperature is increased. When the temperature is increased, the equilibrium position will shift to the left, which is the reactant side. And the reason for this is that the system will absorb the extra heat, favoring the reverse reaction, because it is endothermic. When the temperature is increased, the reverse reaction will be favored because it absorbs heat. Therefore, the equilibrium position will shift to the left, in the endothermic direction. Next, we'll predict in which direction the equilibrium position will shift when the temperature is decreased. So when the temperature is decreased, the equilibrium position will shift to the right, which is the product side. And the reason for this is that the system will produce heat favoring the forward reaction, because it is exothermic. When the temperature is decreased, the equilibrium position will shift in the exothermic direction, which is to the right. Next, we look at the effect of temperature on the value of the equilibrium constant Kc. So for an exothermic reaction, increasing the temperature shifts the equilibrium position to the left and decreases the value of the Kc. So as we saw in a previous slide, the forward reaction of the Haber process is exothermic. Here we have the equilibrium constant expression for the Haber process. When the equilibrium position shifts to the left, the value of the numerator decreases and the value of the denominator increases. Therefore, the value of the Kc decreases. So an increase in temperature for an exothermic reaction results in a decrease in the value of the Kc. For an endothermic reaction, increasing the temperature shifts the equilibrium position to the right and increases the value of the Kc. Here we have the reaction between hydrogen and carbon dioxide to produce water vapor and carbon monoxide. As we can see from the sign of the enthalpy change, the forward reaction is endothermic. And here we have the equilibrium constant expression for the reaction. When the equilibrium position shifts to the right, the value of the numerator increases and the value of the denominator decreases. Therefore, the value of the Kc increases. So for an endothermic reaction, an increase in temperature results in an increase in the value of the Kc. So let's end with a summary, starting first with exothermic reactions. When the temperature is increased, the equilibrium position shifts to the left and the value of the Kc decreases. And when the temperature is decreased, the equilibrium position shifts to the right and the value of the Kc increases. And finally, for endothermic reactions. When the temperature is increased, the equilibrium position shifts to the right and the value of the Kc increases. And when the temperature is decreased, the equilibrium position shifts to the left and the value of the Kc decreases.
So we've talked about concentration changes, temperature changes. Now we have pressure changes. If we change the pressure in the system, it may or may not have an effect on the equilibrium, on the position of the equilibrium. It depends. Are there gaseous products or reactants in the system? If yes, then changing the pressure may affect the equilibrium. If there are no gaseous products, then there will be absolutely no influence of changing pressure on the equilibrium. If there are gaseous products, then it depends on whether the gaseous products, the change that we impose in terms of pressure is done by either adding reactants and products in the gaseous form which is covered in change in concentration, right? That's already done. But if we change the pressure based upon changing the volume, right? If we squeeze it, that increases the pressure, then you get a reaction. But if we simply change the equilibrium by adding an inert gas, that does not change the concentration of any of the reactants or products. So it will not affect the equilibrium position. Okay? So if we decrease the volume, then we increase the pressure and we shift the equilibrium toward the side with fewer moles of gas. It responds by decreasing the pressure. And the only way it can do that is to produce fewer moles of gas. That's Avogadro's principle, Avogadro's law. The volume and moles are related.
The pressure of a system can be changed by either adding or removing a reactant or product, or changing the volume of the reaction vessel. The first point has the effect of increasing the concentration of the reactants or products. The second point refers to Boyle's law. Boyle's law states that pressure and volume are inversely proportional at constant temperature. This can be written in equation form as P times V equals constant K. Changes in volume will affect the pressure of the reaction vessel. For example, if the volume of the reaction vessel is increased, the pressure will decrease. And if the volume of the reaction vessel is decreased, pressure will increase. It should be noted that changes in pressure only have an effect on the equilibrium position when there are different amounts of gaseous molecules in the reactants and products. So next we look at some examples. The reaction we look at is the Haber process, in which nitrogen and hydrogen react together to form ammonia. In this equation we have 4 moles of gas on the reactant side and 2 moles of gas on the product side. This means on the reactant side we have more gaseous molecules, and on the product side we have fewer gaseous molecules. When the position of equilibrium shifts to the side with a fewer number of gaseous molecules, this results in a decrease in pressure. And when the position of equilibrium shifts towards the side with a greater number of gaseous molecules, this results in an increase in pressure. So when we make predictions about in which direction the position of equilibrium will shift for changes in pressure, we need to consider the number of gaseous molecules in the reactants and products. So in the next example, we'll predict in which direction the equilibrium position will shift when the pressure is increased. An increase in pressure shifts the equilibrium position to the right, which is the product side. So the equilibrium position will shift to the right because there are fewer gaseous molecules on the product side, which lowers the pressure. As we saw earlier, there are fewer gaseous molecules on the product side of the equation. When the pressure is increased, the equilibrium position shifts to the side with a fewer gaseous molecules, which has the effect of lowering the pressure of the system. Just like for changes in concentration, changes in pressure do not affect the value of the equilibrium constant Kc. In our next example, we'll predict in which direction the equilibrium position will shift when the pressure is decreased. When the pressure is decreased, the equilibrium position shifts to the left, which is the reactant side. So the equilibrium position will shift to the left because there are more gaseous molecules on the reactant side, which increases the pressure. Because we have more gaseous molecules on the reactant side, an increase in pressure will shift the equilibrium to the left. And once again, the value of the Kc does not change. In our last example, we'll look at changes in pressure when there are the same number of gaseous molecules in the reactants and products. So in this reaction, we have 2 moles of gas on the reactant side and 2 moles of gas on the product side. So the position of equilibrium will not change because there are the same number of gaseous molecules on both sides of the equation. So if we have equal numbers of gaseous molecules in the reactants and products, changes in pressure have no effect on the position of equilibrium. So let's end with a summary. In this table we have change to the system at equilibrium, change in equilibrium position, and change in the value of the Kc. When the pressure is increased, the equilibrium position shifts to the side with fewer gaseous molecules. When the pressure is decreased, the equilibrium position shifts to the side with more gaseous molecules. And changes in pressure when there's equal numbers of gaseous molecules in the reactants and products has no effect on the equilibrium position. And as we can see, the value of the Kc does not change when changes are made to the pressure of the system.
I think that's the last one. Isn't it? Yep. Okay. Let's see. I was going to say something. I think I forgot what it was. Pressure. Oh, he made the point for us. Yeah, I didn't mention before the slide started, when you got equal amounts of moles of gas on both sides, pressure doesn't have any effect at all. There's no advantage to it or changing, so it doesn't change. Okay, so next week we'll do a review of this material, and we'll go in the lab and do Le Chatelier. Okay, that's it.